The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today's focus is probability and statistics. So let's start with probability. Let's look at probability of a binary variable. What do you mean by a binary variable? It can take only two outcomes. So it can take only two values. For example, it could be 0 or 1, head or tail, on or off. Okay? So we are going to call this variable a, for instance. So a could be either h or a is equal to tail. But that could happen, that event could happen with a certain probability. So that by that, I mean the probability is like way of expressing the belief that the particular event could happen. So we could assign a value to that. That is the probability of a taking value h. Okay? Fine. So here, the values of a and b, so here the value of a can be either h or t, which means it has only two possible outcomes. That's why we call it binary variable. However, p of a is equal to h can lie anywhere from 0 and 1, including 0 and 1.
They don't have to be even.
Sorry?
They don't have to be even.
Even?
Even chance, even probability, like the same.
Sorry, I didn't get your question.
Even though it's binary, you don't need to have that they both have like head or tail, the same probability.
OK, we'll look at that later. Like this particular event can take a particular probability. And we'll look at that particular case later. But in general, a probability will always lie between 0 and 1. So, and it can take any value between 0 and 1. So it's the range it can take is continuous. It's not discrete. Okay. However, the value the variable can take is going to be discrete. It can take only a or h, h or t. Okay, so that's why we call it binary variable. For example, take a deck of cards. Here, the value could be, for example, if you consider only one particular suit, then it can be any one of those 13 values. Right? So there, this variable is not binary. However, the probability of a particular event happening is always between 0 and 1. Now let's look at some probability theory, like what you asked earlier is like whether they would be equal, whether the probability of head and tail can be equal. Okay. So let's represent the probability a of h. This can be between 0 and 1. What is the probability of a not happening? So we call it by a bar. Can you, given p of a, can you give me p of a bar? 1 minus p of a. Okay. If there are two events happening, for example, you are throwing two coins, then we can consider their joint probabilities. Okay. So let's say we have a coin A and there's a coin B. So this coin can take two values, as well as this coin can take another two values. Sorry. Okay. We know this A can take H with probability, say assume it's unbiased, so it will be half. all these are going to be half. What is the probability of HT? Okay, so now we are considering a joint event. P of A is equal to H, and P of B is equal to T. Okay? So in probability, we represent it by something like this. PA, do you know what is that? PA intersection B. We want both events to happen. There will be P of A, and in this case, it's P of B. So we could simply say it's 1/4. Why this is possible? It's because these two events are independent. The coin A getting a head doesn't affect coin B getting a tail. So it doesn't have any influence. That's why these two events are independent. The dependent events are a bit complex to analyze. Let's skip them at the moment. So we know like all these probabilities are going to be 1/4. So we looked at a particular condition here. That is A taking head and B taking tail. What about the condition, what about the case where either A or B takes a head? How can we represent that? So it would be something like A is equal to A, or B is equal to or probably at least 1. So that by that I can also represent something like this. Okay, yeah, this is sufficient anyway. So what are the possible events? So these three events could give rise to this probability. It's better if we can represent this in a diagram. So let's go and represent this in a diagram. This is A and this is B, getting, say, head. In one case, both can take head. That is this particular condition, intersection, we earlier looked at. So what is this whole thing? That is either A gets H or B gets H, which is this condition. We call it PA union B. Okay? Is there an efficient way of finding this rather than writing down all possible cases? Is there an efficient way of finding P A union B? From high school maths, probably? No idea? Okay. P A union B is equal to P A plus P B minus P A intersection B. Because if you consider PA, you would have taken this full circle. When you take PB, you would have taken this full circle. So which means you're counting this area twice. So you have to deduct it once. Okay? Great. So this is the basics of the probability. Now, actually, we looked at two events, two joint events here. But we should have a formal way of looking at multiple events. So how can we do that? The first way is doing it by trees. Let's say we represent the outcome of the first trial by a branch. We can represent the outcome of the second trial by another branch from these two previous branches. So this would be H, 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 T, H, sorry, T, H, T, T. Okay? And we know this could happen with probability half. So we know it's again half, 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 half. So this is 1/4. Okay. Suppose we want to do this for an outcome of throwing dice. Then probably we would have 6 branches here. Okay, which again forks into another 36 branches. So there should be another easier way. For that, we could use the second method called grade. We could simply put that in a diagram. Okay, so this is the first trial. And this will be our second trial. Okay. So now we can represent any possible outcome on this grid. For example, can you give me an example where you throw the same number in both the trials? Then what would be the layout of it in this grid? Throwing the same number in both the trials. Because this is the first trial, this is the second trial. Then it would be the diagonal. Right? If you want to calculate the probability, we know the probability is the ratio between the possible outcome, the ratio between the outcomes we expect over all possible outcomes. So here, we know there will be 6 instances in this highlighted area compared to 36 total possibilities. So it will be simply 6 by 36. How can you find the probability of getting a cumulative total of, say, 6? Then again, it will be very simple. It could be 1, 5, 2, 4, 3, 3, 4, 2, 1, 5. Right? So it will be 5 by 36. So either by using trees or grid, you can easily find the probabilities. Okay. Now let's look at few concrete examples. Let's say, suppose we are throwing 3 coins. Then what is the probability of one particular outcome in that trial, in all 3 trials? What is the probability? So assuming that these are unbiased coins. What is the probability of one particular outcome? Because how many possible outcomes are there if you're throwing 3 coins? Consider this tree. First it splits into 2, then it splits into 4, then 8. Right? Okay. So there are 8 possible outcomes. So each outcome will have the probability 1/8. So what is the probability of head appearing exactly twice? How can you do that? Of course, you can write the tree and count. What is the easier way of doing that? Since we know this count, since we know this probability of particular event happening, how can we come up with the probability of getting exactly 2 heads? It could be head, head, or tail. So this is by enumerating all possible outcomes. So it could have been head, head, tail, where we put the tail only at the end. It could have been head, tail, head, or it could have been tail, head, head. In these 3 cases, you're getting exactly 2 heads. So we are enumerating all possible outcomes. And we know each possible outcome would take the probability 1/8. So the total probability here is 3/8. Okay? So this is one way of handling a probability question. Okay? You can do that only because these are independent events and you can sum them. Okay, we'll come to that later. Suppose we are rolling 2 4-sided dice and assuming they are fair. How many possible outcomes are there? 2 4-sided dice, and assuming that each of them are fair, that means unbiased. How many possible outcomes are there? Consider this tree. First, it branches into 4. Okay? In the first trial, it's a 4-sided dice, so there are 4 possible outcomes. So it branches into 4. Okay? Then each branch will in turn fork into another 4 branches. So there are totally 16 outcomes. Okay. So what is the probability of rolling a 2 and a 3? What is the probability of rolling a 2 and a 3? Not in the given order. Not in the given order. Can anyone give the answer? Okay, let's say. So we have to roll a 2 and a 3. So which means it could have been 2, 3, or 3, 2. And we know the probability of each event is 1/16. So this will be 1/16, and this will be 1/16. So the total probability is 1/8. Okay. What is the probability of getting the sum of the rows, an odd number? What is the probability of getting an odd number as the sum of the rows? Now this is getting a bit tricky, because now it might be a bit harder to enumerate all possible cases. So how can we do that? There should be a shortcut.
You either get odd or even.
Sorry?
You either get odd or even.
It can be either odd or even, right? So it would be half. Okay, this is another trick we might be able to use to get the answers quickly. What is the probability of the first roll being equal to the second roll? In the same line, you can think. What is the probability of getting the first roll equal to the second roll? It's quite similar to this. Any ideas? It's a 4-sided dice. There are 4 possible outcomes. This is one case where it could be 1, 1, or it could be 2, 2, or 3, 3, or 4, 4. And if it's like n-sided dice, it will be n, right? So if it's n-sided dice, there are n possible outcomes desired, and there are totally n by n outcomes, right? So we get 1/n probability. What is the probability of rolling? What is the probability of at least one roll equal to 4? At least one roll equal to 4. This is very interesting. These type of questions you will get in the presets and all, probably in quiz too. What is the probability of getting at least one roll equal to 4? Okay, so what are the possible outcomes? First roll could be a 4, and the second roll could be anything, right? Or it could be 4, and the first roll could have been anything. Or both could have been 4, but we would have considered that here as well. Okay? So what we had to do is we had to calculate this probability and this probability, add them, and deduct this, because this would have been double counted. It's quite like this. This is the intersection. We want to remove that, and we want to find the union. Okay? So what is this probability? Since we don't care about the second roll, we have to care only about the first roll, where first roll getting 4, which is 1/4. And this is 1/4, similarly. And this is 1/4 by 1/4, so 16th. So it will be half minus 1/16. And when you give the answers, if it's hard, you can just leave it like this. So this is what we call giving the answers as formula instead of giving exact fractions. Because sometimes it might be hard to find the fraction. Suppose it's something like 1 over, say, 2 to the power 5 into 3 to the power 2, something like this, over, say, 5. You're not supposed to give the exact value in the decimal or even the fractions. You can give such formulas. You can give something like this too, to give the inverse probability of that not happening. Okay. Let's see. Let's move into a little bit more complicated example. A pack of cards. What is the probability of getting an ace? Anyone? 1 out of 2?
Out of 52.
A particular, no, I didn't, ace. Yes, just ace. Huh? 4 over 52. Yes. Okay. Or if you consider one suit, it would have been like 1 over 13, right? You could have considered one suit, and out of, okay. It's the same analysis, right? Okay. What is the probability of getting a specific card, which means, say, ace of hearts? It's what she said, yeah, 1 over 52. What is the probability of not getting an ace? Sorry? 1 over 13. Okay? Okay, this is where we make use of the inverse probability. Okay? So that will come into play very often. Okay, now let's get into 2 decks of playing cards. Okay? What is the sample size? Sorry. What is the sample size of drawing cards from 2 decks of cards? 2 cards, actually. We are going to draw 2 cards from 2 different decks. Sorry? Okay. What is the probability, what is the sample size of drawing a card from 1 deck? There are 52 possible outcomes. So there are not, for each outcome here, we have 52 outcomes there, right? So it's 52 by 52. It's like the tree, but here we have 52 branches. Okay? So eventually you will have 52 by 52. This is where you can't enumerate all possible cases. So you should have a way to find the final probability. Okay? Okay. So in this case, what is the probability of getting at least one ace? What is the probability of getting at least one ace? Okay. This is again similar to this case. Remember this diagram, it's called Venn diagram. Remember this. So what is the probability of getting at least one ace? which means you could have got the A's from the first deck or the second deck or both. But if you're getting from both, you have to deduct it because otherwise you would have double counted it. Okay, so it is getting an A's from the first deck is 1 over 13. Second deck 1 over 13. Getting from both is 1 over 52 by 52. Sorry, 1 over 13 by 1 over 13. You deduct it. Okay. Sorry? Yeah, that's what I explained earlier. You're doing two trials. You could have got the A's from here, and this could have been anything. You could have got A's from here, and this could have been anything. You could have A's from both. Okay? So you should add these two probabilities because we need a case where at least one card is A's. Okay? But the problem is this could have happened here and here. That's why we deduct it. What is the probability of getting neither card? What is the probability of neither card being an Ace? One minus this. Okay, exactly. So it's okay. You're getting comfortable with the inverse probability now. What's the probability of two cards from the same suit? What is the probability of getting two cards from the same suit? Now it's getting interesting. Two cards from the same suit. So how can we think about this? Of course, you can enumerate all possible cases and count. We don't want to do that. Okay. We're going to use the grid here to visualize this. Okay. It could have been a spades or hearts or clubs or diamond. Okay. So we want two cards are the same suit, right? So it's 4 over 16 possible outcomes. Do you see that? So say we are using all the tools available at our disposal. Trees, grids, counting, Venn diagrams, inverse probability. Yeah, you should be able to do that to get the answers quickly. Because you could have actually done something like this too, but it would take more time, right? So this would be a simpler way of visualizing things. Okay. What is the probability of getting neither card, a diamond, nor club? Neither card is diamond nor club. That is tricky. But since we have this grid, we can easily visualize that. Okay? So if neither card is diamond nor club, then it could have been only these two values, right? Which is again 4 over 16. So there are 4 possible cases. Okay? Okay. So what is the summary? What is the take-home message here? In probability, the probability of the belief or the way of expressing the belief of like how many of a particular event happening. Okay. Now, there could be several possible outcomes. Out of those possible outcomes, you have certain number of desired outcomes. How can you find that? You can either enumerate all of them, you can put them in tree, or you can put them in a grid, or you can use some sort of Venn diagram and like come up with some sort of analysis. Okay. Here we start with our belief that the coin is unbiased, or we have a fair chance of drawing any card from the pack of cards. So like we have like all these unbiased beliefs, or sorry, beliefs about the characteristics of each trial. Okay, so we start from that. Then we find the probability of a particular event happening in certain number of trials. But what if we don't have the knowledge about the coin? What if we don't know whether it's fair or not? What if we don't know P of A is equal to H is equal to half? Suppose we don't know that. Suppose it's only P. How can we find that? Okay. What you could do is you could simulate this. You can throw coins several times and count the total number of heads you get. Okay? So it could be n of heads over n trial will give you the P, right? Okay. This is a way of finding the probabilities through a certain number of trials. It's like simulating the experiments. It's called Monte Carlo simulation. And using that, we try to find a particular parameter of the model. You know, like how they actually found the value of pi at the beginning? Pi. It's again using a Monte Carlo simulation. What you could do is, for a given radius, you can actually check whether it lies within a circle or not. You can simulate the Monte Carlo simulation, and with this, given this radius, you can come up with a particular location at random and check whether it's within this boundary or not. Okay? So then you know the outcome. You know the outcomes, right? So suppose this is NA, and the total outcome is tau NT. This gives you the area, right? We know this is r squared, and this is pi r squared. Sorry. Okay. Okay. Why this is 4r squared? This is 2r, right? Okay. So using this, you can easily calculate the pi. Okay. So now, like, since we are going to come up with these parameters through repeating the trials, we need to have a standardized way of finding these parameters. We can't simply say this, right? Okay. Take this example. You know this MIT shuttles, right? A shuttle arriving at the right time, or the time difference between the arrival and the actual quarter time can be like plotted in a graph. So if you plot that, it will be spread around 0, right, probably, or we hope so. Okay. Now, so from this we can say actually it's the mean of this simulation will give you the expected difference in the time, the expected difference in the arrival time from the actual quarter time. Okay? And we hope this expectation to be 0. We call that mean. Mean is taking the average. But this distribution might actually give you some information, some extra information as well. That is, how well we can actually believe this, how much we can rely on this. If the spread is greater, something like this, then probably you might actually not trust the system, right? Although the mean is 0, it could either come early or late, right? So which means it's useless. Okay. Similarly, we can actually, okay, in this case, we have a spread around mean 0. But if you take the score, the marks you get for 600, it could be something like this. It's not centered around 0, right? Hopefully. It's probably, say, 50. Then we actually want the spread to be small or large. We want the spread to be large because we want to distinguish the levels, right? The student's level of understanding, 600. Anyway, so this spread determines what is the variation present in the distribution of the scores. We measure that by a variable called standard deviation. In this case, this particular sample will be different from its mean by a particular value, right? We can express that as xi minus its mean. Let's call the mean mu. So this will be the difference. Standard deviation is summing up all the differences. But the problem is when you sum up the differences, it will be 0, right? The total summation of the differences will be 0, because that's how you get the mean. Because if you expand this, it will be something like this, right? Which will be n mu. Should be equal to 0. So we have to somehow actually take the differences into account. So let's square this. So now it will no longer be 0. Now this gives you the differences, so the squared sum of the differences averaged across all the samples. We call this variance. And the square root of variance is standard deviation. Okay. Now, having a standard deviation, so we know the standard deviation tells you how spread the distribution is. But can we actually rely only on the standard deviation to determine the consistency of some event? Can we? Probably not. Suppose take a class where suppose to take two examples. One is the scores, 50. And suppose the standard deviation is minus 10 plus 10. Okay? So the standard deviation is 10 here. Suppose it lies in this form. Consider another example, the weight of the paper, like say at MIT. And suppose it's centered around 150. Okay. Now if the standard deviation is say 10, then the standard deviation 10 here and the standard deviation 10 here don't convey the same message. Okay. So we need to have a different way of expressing the consistency of a distribution. So we represent it by coefficient of variation, which is equal to standard deviation divided by mean. Now here it will be 10 over 150. Here it will be 10 over 50. So we know this is more consistent than this. the weights of the students at MIT, it's more consistent than the marks you might get or you get for 600. It might be true. Okay. Now, what is the use of the standard deviation, or how can we use them? Okay. Let's look at this graph, where suppose the mean is 0, and the standard deviation is, say, 5. Okay. Consider another example where standard deviation is 10. It might have been like this. Okay. Now, before that, let me sort of digress a little bit. So I can explain this better. We can take the outcome of a particular event as a sample in our distribution. So suppose you're throwing a die. So you get an outcome. You can represent that outcome as a distribution. Okay? So here, there's x, which can take 1 to, say, 6. And we can represent xi as a sample point in our distribution. So I don't know, it might be uniform, probably. We hope. So it's with 1/6 probability, we'll always take one of these values. Okay. But this might not be the case with all events. Right? Okay. So what I'm trying to say here is, you can actually represent the outcome of the trial in the distribution, or you can also represent the probability of something happening in a distribution. How does it work? Okay. In this case, we throw a dice, we get an outcome, we go and put it in the x-axis. It could be between 1 and 6. And it takes this distribution. In addition, what you could do is, you could have, say, 100 trials. Say you throw a coin, you take 100 trials, you get the mean of, you get the probability of getting ahead, and you have that mean, right? So probability of getting ahead for 100 trials, say 0.51. You do another 100 trials, you get another one. So you have now another distribution. So this is a distribution of probabilities. So you can have a distribution of probabilities, or you can have a distribution for the events. We handle these two cases in the p-set. So probably you should be able to distinguish those two. Anyway, so here, in this particular example, let's take this as our mu. Let's take this as our standard deviation. And for the first distribution, let's take the standard deviation to be 5. If the standard deviation is greater, it's going to be more spread. It's going to be more distributed than the former. So here, say the standard deviation is 10. Okay. And the standard deviation is a way of expressing how many items, how many samples are going to lie within those particular boundaries. So for a normal distribution, we know the exact area, exact probability of things happening. So if this is a mu, we know within the first standard deviation, there will be 68% of events lie in that area. Within 2 standard deviations, okay, 1 standard deviation, 68%. 2 standard deviations on either side, it's going to be 95. 3 standard deviations, it's going to be 99%. So if suppose you conducted so many trials and you get the values, and for the in the distribution, suppose mean is 10 and the standard deviation is say 1. Okay. So now with 99% confidence, we can say that the outcome of the next trial is going to be between what? 7 and 30, right? So this is where finding the distribution and its standard deviation helps us giving a confidence interval, giving a probability, giving or expressing our belief of that particular event happening. Okay. We will look at a few examples because you might need this in your preset. Okay, great. So this particular function you have already seen in the lecture. Okay. But we need to understand this particular part. Okay. Suppose you have a probability of something happening. Okay. Suppose you estimate the probability of something happening. Suppose you're given the coin is biased. Okay. Suppose, sorry, unbiased. So we know P of H is equal to half. How can we simulate an outcome? How can you simulate an outcome and see whether it's a head or tail with this particular probability? We do that by calling this function, random.random, which is going to give you a random value between 0 and 1. And you're going to check whether it's below this or not. If it's below this, we can take it as head. If it's not, it's tail. And this will happen with probability half, because the random function is going to return a value between 0 and 1 with equal probabilities. It's uniform probabilities. So to simulate a head or tail, you call that function. You write the expression like that. Okay? Then, if you consider this example, for certain number of flips, we simulate the event, and we count the number of heads we obtain. Okay? And also, from that, you can calculate the number of tails as well, right? If you know the total flips, you know the number of tails. Using that, we are taking two ratios. Now, the ratio between the heads and tails and the difference between heads and tails. We are doing this for a certain number of trials. And we are going to take the mean and standard deviation of these trials. Okay. So here in our distribution, what are we considering? What is going to build our distribution here? The ratios, right? The ratios are events. Okay? And we simulated certain number of trials to get those events. Okay? Then only if you simulate certain number of trials, you can actually summarize the outcome of the events in mean and standard deviation. This is exactly like the difference in the times of the bus arriving and the coded times. Okay, let's check this example. Let's plot this and see. It's going to take a while. Okay, there's another thing I want to explain here. because since we are going to plot, we are going to use Pylab extensively and plot graphs. You need to put title and labels to all the plots you're generating. Plus, you can use this text to actually put the text in the graph. We will show that in a while. Plus, if you want to change the axis to log scale, you can call this command at the end after calling the plot. Okay? Because you might sometimes need to change the axis to log scale in x and y axis. Okay. So this is the mean heads versus tails. And if you can see, the mean tends to be 1 when we have large number of flips. So to get the consistency, we need to simulate large number of trials. Okay? Then only it will tend to be close to the mean. Okay? So this is sort of way of checking the evolution of the series by actually doing it for a certain number of flips at every time. So it's quite like a scatter plot. The scatter plot is like plotting the outcomes of our experiments. Suppose it's x1 and x2 in a graph. So we are going. So for example, suppose you have two outcomes. Suppose you have a variable and the variable causes an outcome. Probability of the coin flip, so P of h, and it can result in certain number of heads appearing, say n of h. Now you can do a scatter plot between these two variables. Then it will be probably spread, but we know that if you increase the probability of heads, the per number of heads is going to increase as well. So it would be probably something like this. Okay. From this, we can assume that it's linear or something like that. But the scatter plot is actually representing the outcomes of the trial versus some other variable in the graph and visualize it. Okay. And let me show the last graph, and we'll be done with that. So this is again, we actually now, instead of putting a scatter plot, we're actually giving the distribution as a histogram and putting a text box in the graph. This might be useful if you want to put if you want to display something on your graph. Okay. I guess we will be uploading the code to the site, so you can check the code if you want later. Okay. Sure. See you next week.